Hello and welcome to this webinar, Quality Assurance and Quality Control, and what is it and how to achieve it. This will be a very interesting presentation, very modern and useful subject, and I hope that it will be very useful for all of you. My name is Ricardo Valls. I'm a graduate from the best university in the world, MGRI, Moskovsky Geological Institute, in 1983. That picture there on the left, that is me with 24 years old. And the picture is black and white because at that time in Cuba, I'm from Cuba, we didn't have color picture. I'm also a professional geoscientist and a qualified person registered in Ontario, Canada. I'm also the author of several books on geology, QA/QC, and the use of artificial intelligence and machine learning. And in today's presentation, we will be talking mostly about this book here, which is Quality Assurance and Quality Control for the Field Work. This book can be bought directly on Amazon.com. And here is the link that you can use to buy the book, and it's a step-by-step illustrated guide of everything that the company needs to do in order to comply with the requirements of the quality assurance and quality control. Also, to obtain a copy of this presentation, you can write me at valsvg@gmail.com, and I will send you the PowerPoint, although there will be a video. Now, why do we need quality assurance and quality control? This story started in 1995. If there are geologists among you that are old enough to remember the dark ages of 1996, it all began with a company called Briex. Briex discovered, in quotation marks, the largest gold deposit in the world. And those shares went from 10 cents up to $286.50 in less than a year. It was just amazing, the rise of this the shares of this company. There is actually a film called Gold, which is basically the truth. They, of course, embellish it a little bit, but basically it's telling the true story. All this started with a guy, not even a geologist, that had a dream. And in the dream, he thought he saw a place in Indonesia where there is the big gold deposit. And this guy sold everything that he had and went to Indonesia to find this place. And of course, he met with a local geologist. In the film, he represented by a Colombian geologist. No, it's not that true. It was a geologist from Indonesia. And they both went together to the field. And I'm not kidding, guys. This picture here, when he's standing and looking at the place, that he stopped there, looked down, and he said, "Oh, this is what I saw in my dream. The deposit is here." And without doing any geological work, any sampling, anything, he just started drilling. Of course, unknown to him, the local geologist started salting the samples. He went to the rivers, he panned for gold, he buy gold from local panners, and he started adding little bits of gold to the core. And of course, when the results start coming, it was just amazing. I mean, it was the biggest gold deposit in the world. So the shares went up there. Now you can see there are two places where the price like fluctuated a little bit, and those were places where geologists said, you know what, this is too good to be true. And we must say that we're Canadian geologists, the mining analysts, the first one to raise awareness, say, okay, there is something that is not really good here. It cannot be that amount of gold. But the people wanted to believe. So no matter what, the price kept going. Then the big companies wanted a piece of the play. So they wanted to do a joint venture or just buy the mine from this guy. Now, we must say that the guy itself, he didn't know that the samples were salted. He really thought that he has discovered the biggest gold deposit in the world. But as part of the due diligence done by these other companies that were interested in buying the property, they went there, they took samples, they came back, nothing, no gold at all. So that was the second big fluctuation. But again, there is no worse blind person than the one that doesn't want to see. So it continued to grow up. And then a group of mining analysts and geologists from basically Canada, they start looking at the core with a microscope, even with a lens, and they noticed that the gold were nuggets, like they were rounded. Basically, it was clear that this was gold from a river, not from the rock. So basically, in 3 to 4 months, the company went from $286.50 down to zero. It was a catastrophe. And this was in at the end of 1996. And at that time, it was almost impossible for a junior geologist to find work. People stopped believing in mining. All the money went out from mining, and it went into the dot-com companies that were flourishing at that time in the States. So it was a catastrophe. Now, again, were the Canadians, the geologists from Canada, that found the solution for this problem. And the solution was two-sided. First, they created what is called the National Instrument 43101, which is a technical document that has a format uh, that describes in very objective way, describes the deposit and the concept of the qualified person. And we will talk a little bit about these two bases right now. But before that, and this is like a bonus for you guys that are listening to this presentation, go to sim.org, www.sim.org. That is a Canadian Institute of Mining, Metallurgy, and Petroleum. And you will find there two very important places. One is the definitions of the standards, which at this moment, they are universal for all the technical reports, being it National Instrument, York, or Separac, or whatever. All of them use the same language. But more important is the same best practices guideline. These are the best exploration guides to use. So any geologist should have this at hand. It's something similar to what in my times when I was studying at the where the SUSN, but for our more modern, more capitalistic side of the story. Now, this graphic is very important, and for you, for geologists that work as QPs in everywhere, you need to show this graphic to your potential employers. Usually, like 5 years ago, or a little bit more, 5, 10 years ago, when I was called to do a 43101, I was called down here. When all the work had been done, they called me and said, well, we need a 43101. Okay, so when I got there and I found errors and mistakes, they were not, they were too late. They are there. And let me put you an example that was really, really clear. Like 7 years ago, I was working on a gold mine in Colombia. This mine has been producing gold for 75 years. So it's a known producer of gold. The company was bought by an American, the mine was bought by an American company, and they wanted to list the property on the Toronto Stock Exchange to get public funding. So they hired me to do the 43-101. So they called me here. When I got there, I discovered that in 75 years, no one has ever done a quality control in the results, which doesn't mean that the results were not right. What means is that the result that we could not use those results in order to do a resource estimation because they are not verifiable. And this is very important. So I called the president of the company and say, you know what, I'm sorry to tell you, but you don't have data to do a resource estimation. I said, what are you talking about? I have more, and he had more than 275,000 points of data from within the mine. I said, yes, you have all those points, but you don't have quality control. So we cannot verify, we cannot validate this data. Therefore, it cannot be used for resource estimation. Usually, when this happens, because it happened to me more than one time, the company gets very angry. They just fire me and they try to find some other geologist that will do what I didn't do, but nobody will do it. So basically, they come back to me. But this guy was different. This guy said, okay, what can we do to solve this thing? So we redid the sampling of the mine, we twin holes, blah, blah, blah. Okay, we spent a lot of money, but we were able to validate the original data, did a 43-101, and now the mine has been already sold to a group from China. So it is important that the qualified person, and this is part of the quality assurance, it is important that the qualified person will be involved in the project from the beginning. So all these standard projects, standard problems will be dealt before it is too late. The 43-101, as I said, is a very interesting uh, report. It's a technical report. It must be technical and scientific, but it must be written in a way that a normal investor will be able to understand it. So it's a really good balance between science and easiness of understanding the information. And it has a structure that must be used, mandatory. And this, what you see here, are the items that are included in a 43-101. These ones here, from 15 for 22, are for reports that are working with advanced mines that have already reserves, not only resources, or that are producing, etc. So the only thing that may not be included in the 43-101, if you're working on a new project, a grassroots project, well, these points will not be needed, but you need to put them and say not available, not available, or not applicable, not applicable, not applicable. But the structure must be exactly as it is here. The first thing that the reviewers at the stock exchange do when they receive a 43-101 is open it, go to the table of content, and check that all these items are there. Now, you notice that there are some that are in bold, like summary, introduction, reliance on its expert, data verification, blah, blah, blah. These in black are the most important one, in the sense that this is where the more care we need to put for the quality assurance, the quality control, especially item 12, the data verification. That's what happened to this other company that I mentioned before, that they have more than 250,000 data, but they didn't have anything because the data was not verifiable. Okay, so we will be talking a little bit about all these things. Again, the webinar is more oriented to quality assurance, quality control, but this is part of quality assurance. So data verification. One of the things that is mandatory in any kind of technical report, being 43101 or York or whatever, is that a qualified person must visit the property physically. He must go to the property, take a picture, say, I was here. And also he needs to verify that the property legally belongs to the client. Also, and it's very important part of the data verification, is to check the accuracy of all the data. Now, the 43101, I always tell people, the clients, the 43101 is like a picture that you take of the company at the moment of the visit. But there are some items like the data verification that you need to not only just tell what happened, but give your opinion. Okay, so there will be an opinion of the QP on the report, and that opinion, that this little paragraph here, based on the data verification performer, blah, 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 this could kill a report. If the QP says that, you know what, we are not confident on the quality of the data verification, and that is the end of the report. This is very, very important, okay? Now, what are the type of data verifications? And you will not be surprised. Maybe some of you already have seen this, but I will go to the field and I will select 4 or 5 drill holes, get the information from the database, and go to the field and check first if the if the hole is in the place that they say it is, if it is oriented in the azimuth and dip that is described. Sometimes they are not, okay? And for example, the inclination, you have to check all these things. And during a site visit, it is important to also visit the core shack. Core shack for me is the heart of the company. And whenever you need to do the independent sampling that you always need to do, best place to take the samples is from the core shack. I do have a video, and some of you know me a little bit already. I have a channel on YouTube called Geology, where I put several videos about geological problems, and one oriented specifically to the work of the core shack and how to organize it and make it work the best possible. But independent sampling, what I do, I select 3 sites, one that report high values of gold, one that reports low values of gold, and that one that reports no values of gold. And I take samples and send it to the lab. Of course, those samples are on my hands all the time. I personally deliver to the lab, and I get the result directly from the lab. And of course, nobody will be angry if a sample that I took from a barren zone came with some gold. Of course, it's a problem, but it's a good problem to have. But sometimes a sample that you took from a high-grade zone comes back barren with no gold or little gold. Those are big problems. And as I said, one little error like this could kill a project. You also need to do what is called the laboratory audit. Laboratory are our best friends, so we need to do several visits and work with them. So there is geologist here, Harry Parker, that say assume nothing, check everything, trust no one. But I prefer the saying from Lenin, Daveriai, no praveriai. More easy than that. So let's start talking about quality assurance, quality control, etc. So we're going to talk about how to design a quality assurance, quality control program. What are the most common types of quality controls? How we organize the program of a QA/QC in the field, how we determine the quality of the QA/QC. It's not only taking the samples, but it's also checking, well, do we have a problem or not? Then I will add these flow charts of how to organize the work for rocks and soils. Basically, those are the two more important type of rocks of sample that we use. And I will dedicate a little bit of time to one of the most important part of quality assurance, which is how to name rocks and alterations in the field. That will be the last part of this presentation. So wait for it. Don't go away. This is very, very useful and very, very important. So to start quality assurance, quality control, we of course need to have it written or in a video or some way. It cannot be just word of the mouth. There must be a set of documents that explain how we'll be working, etc. And it must explain why, what are the most common errors that we receive, and why is this is so important to have it in a written or a video. Because when you get new geologists that start working with you, usually they will need like 2 3 months before they can start working on their own. It doesn't matter if they are the best graduates from whatever the best university. Very few young geologists can start working in the field directly. They need training. They need to gain experience. And that training and experience is given by older geologists that, to tell you the truth, have much better things to do than to teach the young ones. So having this all in a written or a video, it liberates a lot of work from the old geologists. Now, let me show you some of the, the quality assurance that you can have. This here that you're looking at, this is a sample card, a very, very simple sample card that we use in the field. Now, because I'm graduate from ENGRI, we were taught, and I always try to do this, to do what is called the complex system approach. I don't go first to the field to do mapping, then go again to do soil sampling, then go again with the geophysics. No, we create a team that is composed by a group, like the mapper, the geophysicist, the geochemist, etc. group, and we go one time in the field and we do all the work at one time. Yes, of course, you spend more time per point, but you save like 2/3 of the exploration time, you save it. So it is important to be able to collect all the information possible in every time you go into the field. Now, this card here is for in cases where you're working with very low tech people. Basically, they know how to read and write, and they will put a cross for the signature. Okay, so here you see you have the coordinates, okay, the elevation, the depth, the color of the soil. I mean, they just need to tick the color that is more similar to this. They use a capometer, which is a very simple instrument. They put it here. If they have a radiometer, a oscillometer, they will put the values here. Now, we also use a technique, and I will talk about this, the temperature. And again, there is a video explaining all this thing in more detail, but I have discovered mm, from many, many, many years of working that using a simple thermometer, a laser thermometer, and you measure the temperature on the surface and at the bottom of the little hole that you do for the soil sampling, that difference in temperature is related to demineralization. Why? Very simple. All the deposits, especially in the tropics, but almost everywhere, they have bacteria, and this bacteria eats the sulfite and they fart. And this fart is methane and other hydrocarbons, which are cooler than the surface of the ground. So if you don't believe me, please do it yourself. Take a place that you know that has a mineralization, make a line, and take a series of measurements from the surface and down 10 centimeters, 50 centimeters. Sometimes the difference is more than 15 degrees Fahrenheit, and it works like a charm. It really works. So sometimes with just a thermometer, we can have an idea of where the mineralization may be. Well, also the date, the acidity of the ground, pH. If you don't have a river nearby, you can always take a test tube, put some distilled water, put some soil, mix it, and measure the pH. Again, it's not very scientific, but it will give you differences on pH. When you're working on top of the felsic rocks, it will be more acid than when you're working on top of gabbros. I guarantee. And the last combination is just to describe the composition of the sample. And again, we will train the locals, say, okay, how do you determine sand, clay, sandy clay, or carbonates? Okay, you just take a pinch of the soil and do like this in your fingers. If it is plastic, that is clay. If you feel the grains, that is sand. And you just put a little bit of ACL or lemon juice, and if it fizz, that's carbon. So as you can see, it's a very, very simple card, but it allows you to get a lot of information in a very systematic way, even when you're working not with advanced technical people. Now, if you are working with geologists, technical geologists, you can use more complex cards like these ones. By the way, there is a book, not a book, a paper about these cards. These are cards that are the size of, you can put it on the pocket, and you have all possible information from the location of the sample, the location, the type of relief, the the type of I mean, absolutely everything that you can think about of sampling, of the sample information sample, you can put it all in a code form in this little card. This is, for example, for the soil sampling. This is for um, this one. Yes, these are for litho geochemistry. So this is for soil. This is for litho, and again, it has a series of advantages. First of all, systematicity. Everybody will go and describe the same things. They will not forget to describe third, because for those of you that work in the field, you know perfectly well that it's not the same at 8 o'clock in the morning when you're just starting to work, then at 4 o'clock in the afternoon on the rain, bitten by mosquitoes. At the time, you are only thinking, where is the damn truck to go back home? But using this card, it will force you to answer all these questions, which, by the way, with just a couple of weeks of using, you will remember by heart what everything means here. The other advantage, big advantage of the thing is security. If you don't have the code, you don't know what 122C means. And another advantage of having this system is that you don't need to translate anything. You can have the code in Chinese, in Spanish, in English, in French, in Russian, whatever. So you have the code in whatever language you want, then you can understand these cards. So this is the kind of quality assurance methods that you need to implement if you want everybody to be working the same way. And this is very important. Now, for the drill holes, that is really very complicated because there is so many things that you need to do when dealing with a core. And I created this, it's like a booklet. For each hole, you will have a book that will have this composition, and every page will have some information for the drill holes. And this is the best way to compile the information. Okay, so again, examples of these things, I have some of them online. Some of them, this is my job, this is what I sell. So I can always advise, but this is what we offer in Valcio Consultant. So for example, this is the drill request. This is the sample control, which samples are, you know, what type of control we have, the blank, the standard, the duplicate, where, from where to what. Absolutely everything is registered here. By the way, this company was a company in Armenia that we were working, and they are really, really well prepared. I have prepared their group that is really, really good. That was in 2013. Now, another quality assurance moment. Sorry. And for about this, we're going to talk at the end of the webinar in more detail how to name rocks and alterations. And I created a series of flowcharts and diagrams that will allow any geologist, actually even a guy that is not a geologist, because the questions are really simple, to come down to the name of the rock. And you probably have heard the joke that if there are three geologists sitting at the table and they put a rock and they ask, what is that rock? You will get four answers from three geologists. But this way, you will get just one. And this is based on the British Geological Service system that they created, which is absolutely amazing. But again, this will be the end of the conversation. I'm just going to show you these kind of graphics. Okay, these are posters that I will put on the wall of the core shack. So during the description of the core, you can just check there. Oh, okay, this is a calcirudite, or this is a tonalite. No problem. It's very simple, and you will see how it works. Similarly, you will have posters for all the type of deformation, structural lineament, etc. These are things that is very good to have it like posters so you can check. You don't have usually too much variability within your project. So maybe you will be working just with one of these four charts. Within the maybe two or three examples, but it's good to have them all because you never know where you're going to be working. In all these charts and flow charts are in the book that I mentioned at the beginning. Uh, well, Anton, I usually have a recess here. I will continue. Just let me drink some juice.
Yes, sure.
So let's go.
Okay.
Oh, no, we are not talking about this. Okay. One, two, three.
Mhm.
So let's talk about the most common type of quality control samples. We have duplicates, blanks, standards, and external controls. Each one has a specific purpose and a specific amount of, of sample that you take in each project. Now, duplicates. There are different type of duplicate. There are the field duplicates, which almost nobody has the time to do. What is a field duplicate? A field duplicate is after the work is finished, a senior geologist will go again to the field to certain places and take a sample exactly where the previous sample was taken. That is called a field duplicate. As I said, in the industry, almost nobody has time for that, and it basically is not that important. We are talking here about the duplicates during the sampling the of the source or the core from the drill hole, and the objective is to see the reproducibility of the results, which is very important. There is precision, um, sensibility, and reproducibility. And it's practically impossible to get the three to the top. But if I, as a geologist, a field geologist, not an academic, as a field geologist, they ask me, what is the most important for you? I will say reproducibility. Because the fact that I take a sample here, it gave me 5 grams per ton, and then I take a sample, same place, that give me no gold. That is a sample that I cannot work with. So we have duplicate that checks basically the reproducibility. Then we have the blanks. The blanks are really important. Blank is a material that we absolutely know that it has no mineralization, the mineralization that we're looking for. Let's say we're working for gold, we need a sample that will not have gold, but we need to be sure that it doesn't have gold. And I will tell you a story. I was working in Colombia, and one day we are going to the field, and on their way, I remember I forgot to bring my blanks. Okay, we are passing by a construction, and they have sand, gravel, etc. So I stopped the car. I came out. I asked the guys there, can I grab a little bit of sand? They say, yeah, sure, take it. So I grabbed some sand from the construction site. We go to the field, do our work, blah blah blah. Send the sample to the lab. All the blanks came with gold because this company was picking the sand downstream from a producing gold mine in the Magdalena River. So you need to make sure that your blanks are really blanks. For that, you can buy it. There are companies that sell blanks, but you could use material like, you know, bricks. Take some bricks, pulverize them, and use them as blank. It's very difficult that a brick will have gold or copper or anything. Or you can have some potting soil, the black soil that you use to grow flowers, etc. That black material that is pure bitumen, it is very difficult that it will have gold. And the blanks are used to check that the lab is cleaning the machines as they should. And basically all the good labs works perfectly well. They know. So they will clean with air every sample in between samples, and then they will use their own blanks every 5 or 10 samples, unless you are telling them that you're sending mineralized material, in which case they will clean the crushers and the pulverizer every sorry In that case, they will clean the samples and the pulverizers, every sample with sand, quartz, the blanks, whatever they are using. If a blank comes with a value of the metal that we're looking for, let's say gold, then it means that the lab didn't clean well the machines, and there will be some problems that we will talk a little bit later. The third type of control is a standard. The standard is very important. It determines the precision of the lab. So if your standard is, let's say, 2 grams per ton of gold, the lab must report 2 grams per ton of gold plus minus 10%. So 2.2 to 1.8 is considered a good result for the standard. Usually it's less than that, but that's the limit. Standards are bought usually, or they can be created. And the best ones are when you create your own standards. And let me explain you why. The standard depends a lot on the matrix of your samples. If you're working on a limestone area, it's not the same as you're working on a granitoid. The matrix is different. So you need to have standards that respond to the matrix of the place that you're working. Now, the other thing, misconception, is that you need to have 2 or 3 different standards. You need to have one standard for high grade, medium grade, and low grade. No, you don't need that. The lab must be able to determine a low value of gold between a highly mineralized area, the same way that it should be able to determine a medium or a large value of gold between a barren terrain. So you really only need one standard, whatever it is. But it doesn't matter the grade because the cost is the same. Now, as I said, there are companies that sell standards. One of the best one is CAD, like CAD, like Canadian CAD laboratories. They are the only ones that I know that sells standards for multi-element analysis too. You can buy it or you can make your own. Now, if you make your own, that is the best standard possible because it's your rock, but it is very expensive to do it. It doesn't make sense if you are just doing a short exploration. But for example, I was working in Guatemala for nickel laterites for many years, and we decided to make our own standards. And what you do, you get like, I don't know, 50, 100 kilograms of laterites, okay? And then you find a lab that will pulverize all that down to 180, 200 mesh. And when you have all that material pulverized, you take 10 samples and send to one lab, 10 samples to another lab, 10 samples, like 5 different labs, all high quality labs using the same methods. You get the results and you get an average of what is the average value of the nickel plus minus the standard deviation. And that is the best standard possible. But as I said, it's very expensive and it's not worth it if you are doing a short work. I mean, this is when you have already deposit and you're going to be there for years, like we were in Guatemala over 3 years working. And the final type of control is external control. And the external control happens at the end of a program. Not at the end of the project, but at the end of the program. Let's say you have a soil sampling program. When you finish, you get all your pulp bags, and then you select 1%, one sample every 100 of the pulps, and you send it to a better lab than the one that you use. Let's say, for example, usually in Canada, SGS is considered the arbitrage lab. I mean, they are the best. Okay? They are very expensive. So I don't use them for my current job, but I would use them for external control. And I will use other labs like ACT Labs, ACME, Inspectorate, Bureau Veritas, whatever. It must be, it doesn't need for the 43101, it doesn't need to be certified, but it's better. Okay, so I will use one lab, send all my samples there, and then I will send this external control to a better lab using the same method. If the results are different, there are, as you know, there are two types of errors that you can have. You can have a systematic error that all the results from the other lab are higher or lower than ours. That's easy because it's systematic. You can determine the regression and adjust your data. Or worst case scenario is a casual error. Sometimes goes up, sometimes goes down. And in that case, you need to let both labs to fight it over. But if, let's say, SES determines that yes, the other lab made an error, they need to repeat all the samples from their own pocket price. I mean, this is why it is so important to be a good friend of the lab, to have a contract with the laboratory, not only checking how fast I'm going to receive the result. No, what is going to happen if anything fails? And this little table here just tells you that I will get, ah, actually the duplicates. You see, I have a sample every 40. Usually duplicates, I will have a sample every 20 if it is not gold. If it is copper, lead, zinc, iron, whatever, I will take a duplicate every 20 sample. I will not take a duplicate every 20 sample for gold for one reason. Gold has an inherent nugget problem, and it's practically impossible to get two duplicates from a gold deposit that will be analog. So I will talk about this a little bit more later, but I only take one sample every 40, blanks, one sample every 33, standards every 25 or 50, and the standard control every 100. And I will add a code to the little booklet. Remember the booklet that I showed you at the beginning, or the card, the codified card? It will have a letter indicating what kind of sample will be duplicate, blank, standard, external control, or regular. Regular, I usually don't put anything. So, what is the best way of distributing the blanks, the duplicate, and the standards in the sample, in the, let it be soil samples or core samples? The best way would be casual. You know, I will put the blank here, I will put the standard there, or geologically oriented. I will say, I see here, this has a lot of chalcopyrite. So I will put a blank after this mineralized zone to make sure that the next sample doesn't get contaminated by whatever mineralization will be in this section. Okay, that is the best way, but that is the guarantee way that you're going to get a mistake. We are going to make a mistake, a human mistake. We will send the wrong sample, the wrong blank, etc., etc. So, especially in the industry, I would recommend to use a systematic way. As you can see here, for example, I said I'm going to take a blank every 33 samples. So my sample 33, 66, and 99 will be blanks, always. I will take a sample every standard every 25 sample. Okay, samples 25, 50, and 75 will be standards. I would take duplicate every 40 sample. Okay, sample 20 and 60 will be duplicates. And that will be always. Now, there are three advantages of doing this way. First, limit your error. There's practically no way you can make an error if always these are the samples they're using. Second, as soon as you get the result from the lab, just by looking at the paper, you will see if there is an error in the blanks or in the standard, because you know already that sample 25 must be 1, and if it comes with 3, that's an error. Or the sample 33 must be a blank, so it comes with 3 grams per ton of gold. Well, that was an error. So that's the second one. And the third one, for as long as the lab doesn't get a copy of this list, you're okay. And you can change the numbers every so often. Now, this is the part that takes a little bit of work. What, how to prove that we have a problem with the blanks or with the controls? Okay, very simple. Blanks must have no value of the element that we're looking for. So we use the low detection limit of the lab. Let's say SES, the low detection limit for gold is 0.05 gram per ton. Okay. If a sample, blank sample, comes 10 times higher than the below detection limit, then that blank failed. So if you get a sample that is 0.5, 0.6, 0.7, that blank fails. Okay, that's simple. 10 times the lower limit of detection of the element for that lab specifically. And remember that different labs have different low detection limit, even different methods have different low detection limits. So it's just 10 times. The duplicate is a little bit more complex. You need to do some statistics. We need to use the student criteria and the Fisher criteria. You take all your samples, all the duplicates, and you do the statistic, the average and the standard deviation, using the criteria, the student criteria to determine if these two batches of sample are analog by the mean, and using the Fisher criteria, you do the same and see if the two batch of samples are analog by the standard. If it fails one of the two or both, then we consider the duplicate fail. Now, with the standard deviation, it's very simple. It's the value of the standard deviation plus minus 10%. So you use a standard that is 2, any value between 1.8 and 2.2 is considered okay. Anything above or below that is an error, and we can say that the sample failed, the standard failed. Now, what happens when a sample fails? Sorry. What happens when a sample fails? If a blank fails, the lab must repeat 3 to 5 samples from the sample that failed to the next 3 or 5 from the original material, not the poll. From the original material, they need to do it again. Again, this is paid by the lab because they made a mistake. If a duplicate failed, basically we do nothing. We just call the lab and tell, you know what, we are looking here and your duplicates are, not working very well. I'm talking the case of gold, okay? Because if the duplicate fails for any other metals like copper, lead, zinc, the lab must repeat that sample that failed and send you the result. And usually you will make an average of the two results, and that will be the value for that sample. But in the case of gold, as I said, because of the nugget effect, it is very difficult to ask from the lab to get all the duplicates correctly. So what we do, if you are working with soil samplings, okay, you can increase the volume of the samples. Let's say you were grabbing 100 grams of soil, take 200, take 300, take 500. I mean, take more sample, because the bigger the sample, the less the nugget effect will be. But as I said, duplicates for the case specific of gold are very tricky. So I will inform the lab, we are having this problem. I'm going to increase the volume of the samples. If it is a core, we are we are limited by the size of the core. We can only send half of the core. We cannot send the whole core because we need to keep something. By the way, if I have time, I will talk about a way that I use to prepare duplicate from core, which is guarantees the best possible core. Now, if a standard fails, and that is really a big problem, let's say we were sending one standard every 50 samples. If a standard fails, the lab needs to redo, not from the original material, but from the pulps. They need to redo 25 samples before and 25 samples after the standard that failed. And that is under nickel. They need to pay for that. And that is why it's so important, the standard. Now, what happened is that the lab also use its own standards, and they will not release the results until the standards pass their test. So usually what happens, you have this standard here that failed, your standard, but 5 samples before there was a lab standard that didn't fail, and 10 samples after there was another lab sample that didn't fail. They don't need to repeat 25 and 25. They only need to repeat the samples that are between the two tests that didn't fail. And again, this is paid by the lab. One thing that I always tell everybody, that when you find an error, being blank, duplicate, or standard, always look first for the human error. Check that the sample that you sent was really a blank or a duplicate, because we are human and we are prone to make mistakes. Now, here, this will be in your video, and as I said, I can send the PowerPoint to everybody that wants to. They can write me at valfg@gmail.com. These are flowcharts for soils and rock, how you need to organize the work with the lab. So before you start working on a project, you prepare a document, a contract with the lab, and you include these flowcharts, which tell you where are the duplicates and the standards, everything, where it's going to be included. The lab love this, because when the labs understand that the geologists understand what they are doing, they will work with you. Okay, so this is really important. Now, second, we are about to finish, and this is the most important part of this presentation, which is naming the rocks and alteration in the field. And you probably know that there are several diagrams, like ternary diagrams or rhombs, if you know the model composition of the rock, it will tell you what the rock is, etc., etc. But the British Geological Survey were the first one to realize, or at least not to realize, but to write about it, that there is a big difference between a guy sitting in a lab with a white t-shirt, air conditioning, tea, all the result of the XRF analysis, microscope, etc. It has all the information, all the commodities to find the name of the rock, compared to a geologist that is in the middle of the field on the rain or beaten by mosquitoes, etc. So it's different. So they define 7 fields of degree of description. We found between field 4 and 5. Now, As I said, if you are interested, you can go to the British Geological Survey. They have these booklets there, how to uh, name all type of rocks, sedimentary, metamorphic, igneous, even man-made rocks. Everything is there. But this, I found it a little bit too scientific. So what I did, I studied all that material and I combine it with the Canadian standard way of describing an outcrop. And I do like the way geologists here work. And this is the most important part. Oops, sorry. The most important part of the description. We are going to go alteration, then the name of the rock with the qualifier, then we will talk about texture and then mineralization. Now, since I studied in Russia, in former Soviet Union, I know that the concept of texture is is structure. So we're talking here for the Russian speaking, we're talking here structure, not texture. So the other big thing that the BGS, the British Geological Survey, did, they defined two different names. One is called a root name, and the other one is called an approved name. Okay, and the difference is you have a rock in your hand and you're absolutely sure that it is what you think it is, like it is dunite, and you are 100% sure, then you use a root name. You call it dunite as a root name. If you are not sure, you are working in the tropics, I mean, the rock is completely oxidized, etc. You think it is a dunite, but you're not absolutely sure, then you can use an approved name like ultramafic rock, okay, which is not a root name, it's an approved name because it's like a level, an upper level of description. All dunites are ultramafic rock, not all the ultramafic rocks are dunites. So this is what helps you to get the same names for the rocks, even when different geologists are working in the same place. And we will see one of those flow charts, analyze them. So we have root names, we have proof name. When you are typing, your report, any root name, you're going to put it in bold and underline. Any approved name will be bold, and the qualifier will be in italics. If you are handwriting, I mean, your field book by hand, then the root name will be underlined, the approved name will be normal, and the qualifier will be within quotation marks. So basically, this and the use of hyphens are the two things that you will need to remember. Naming the rock is one of the most important tasks of geology, and especially when you're working with teams of geology, it's very difficult to get to one name. And everybody knows the joke of four geologists sitting around the table, and they ask, "What is this rock?" One will say, "Well, for me, it's a plyogranite." No, the other one say, "No, for me, it's a granite." Then the third one would say tonalite, and this one will say, well, for me, it's just a polymitic sandstone. So it is very important to have a way of naming the rocks that will be standard, that will be easy for everybody to use at the same time. And you probably are very aware of this kind of graphics. Like if you know what is the sag composition, how much plyoclast, how much olivine, etc., then you can plot it in this ternary diagram and know that, oh, this rock is a lersolite. Or you have the exact percent, how much olivine there is, and how much pyroxene, etc., then you can use these tables to define the name of the rock. But for that, you need to have that information, and that is not something that you have available in the field. Now, What I'm going to be using here is the British Geological Society rock classification scheme. They have uh, booklets for igneous rock, metamorphic rock, sedimentary and volcanosedimentary rock, and even man-made rocks. Whoever is very interested in this, I strongly recommend you go to the BGS and you download these booklets and you read them. Okay, but I found that they are a little bit too academic. And what I have done the work of downloading everything, reading everything, and try to make it more workable for the geologists in the field. Now, there is it is clear for everybody. It is different for a geologist sitting in his lab with microscope and all the results from the assays, etc., to determine the name of the rock. Compare that to the geologist that is in the field, is bitten by mosquitoes, it's already 4 o'clock, and he's thinking more, what is the truck than what is this rock? So this is clear. But
Yes.
where the
Yes.
British were the first ones to say, okay, there is a big difference. So they define 7 levels from the guy in the lab to the guy that is eaten by mosquitoes alive, and what are the different names of rock that you can do. Our normal work, we fall in fields 4 to 5. So what I did, I took these groups, this description, this um, booklets from the BES, and I added that. First of all, I simplified a little bit to make it more workable for the field geologists, and I added that to the system that is used here in Canada for the description of an outcrop. And the system here is based first by the description of the alteration, then the name plus the qualifier, then the texture, and then the mineralization. As I said before, the British also determined 2 levels of names. One is called the root name, and the other one is called the approved name. And the root name, as I said before, I'm just repeating myself a bit here. The root name is when you're absolutely sure that the rock that you have in your hand is a dunite. Okay, so you call it dunite, and that is a root name. If you're not sure, then you can call it an ultramafic rock, because that is the name on top of it. So all dunites are ultramafic rock, but not all ultramafic rocks are unites. Okay, so let's start with this schedule. We start with alteration, and we are referring to hydrothermal alteration, not the weathering. So we define several types of alteration, like pervasive, selective pervasive, vein, veinlet, fracture, box, disseminated, and selective. You have a code, we have an intensity. Pervasive is when, for example, serpentinite. Serpentinite is a pervasive alteration. The whole rock has been converted into serpentinite. Selective pervasive is when one mineral, or more than one mineral, only gets altered. For example, you get a liswinitization where the plioklast turns into calcite. So that is a selective pervasive classification, alteration, sorry. So vein, veinlet, that is classical, fracture. All the other ones are very simple to do. And the intensity, this is for when you're doing your description and you want to put that information in the computer. Computers understand numbers better than letters. So that's why I offer you the 2 things. So how you do this, how you use this, how you describe, and I have here 3 cases. So PA9 SERP means an almost completely serpentinized rock, like 90% pervasive serpentinization. Here you have SP SER8-CHL2, which means a selective pervasive alteration of the rock that is now composed 80% of cerussite and 20% of chloride. The dash means 2 or more different alterations at the same time. The other point is the semicolon. This one here, the period and the comma. In that case, you have, for example, D plus VT Chi8, column P cert 9 means a sequence. This is when you are describing an outcrop, and you can see there is a sequence of alteration that starts with a very intense, disseminated, and invariant potassic alteration that evolves into a very intense, pervasive sericitic alteration. So the dash means at the same time, the semicolon means an evolution, a sequence. Okay, so that is the alteration. Now, this is what I was saying about the general codes, the names, root names, approved name, and qualifiers. When you are typing your report, a root name, you will put it on bold and underline. The approved name will be just bold, and the qualifiers will be in italic. If you are writing in your notebook, you will underline the root name, you will write normally the approved name, and you put the qualifiers into quotation marks. Now, there is also the hyphen, and in this case before, the hyphen here is meant that there are two types of alteration at the same time. The hyphen here is used again to join approved names with qualifiers or qualifiers with qualifiers. This is not complete. The only time when you will not use a hyphen will be to add a qualifier to a root name. Okay, and we will see some examples, and you will have this to remind you. I'm telling you, after 3 or 4 times that you do this, you will remember. Okay, you can use hyphen for everything except to join a qualifier with a root name. That's it. That's the rule. Okay, so what are the qualifiers? Qualifier means something that is not usual. For example, you cannot say that a granitoid is quartz rich. Yeah, all granitoids are quartz rich. Okay, so qualifier, a quartz rich cannot be a qualifier in that case. But you find, for example, a rock that normally its color is black, okay, like I don't know, any rock that's normal color is black, and you have a different color. Well, in that case, that different color could be a qualifier. That's one type of qualifier. The other type of qualifier is the leuco or mela. Leuco is when a rock is clearer than it should be, and mela is when the rock is darker than it should be. For example, you can have a leuco gabbro, the gabbro that is lighter, or a mela granitic rock. If you have a lot of magnesium in that rock, it looks darker than it should be. Okay, now the color itself, as I said, the color itself can be added as a qualifier. For example, you can say a brown obsidian. Obsidian is usually black, okay? But there are red obsidian, there are gray obsidians, there are brown obsidians. So that in that case, the color is not usual, so you can use it as a qualifier. Okay? Those are the qualifiers. Also, if there is an abundance or a lack of a certain mineral. For example, let's say you have a granitic rock that has a lot of quartz or a lot of albite, whatever. You can always say albite bearing quartz, or sorry, albite rich quartz, or mica bearing granite. So again, if you have a lot of albite in the granite, you can say albite rich granite. Or if you have too little mica, then you can say mica bearing granite. So The same thing happens for the grain size. If it is normal, it's not a qualifier. Only if it is too much or too little, or too big or too small. Those are the qualifiers. Think of qualifier as an adjective that will become part of the name of the rock. Now, this is from the book from the British Geological Survey. This is how they classify the normal crystalline rocks or igneous rock. I don't like it for one reason only. Yes, they start very well with big division, quartz grain, if it is more than 2 millimeters, or fine grain if it's less than 2 millimeters. But then they are asking you for the modal composition of the rock. And again, in the field, especially in the tropics, you will never be able to define uh, the proper amount of quartz, albite, and pyroclast in a rock. It will be just a red stuff in your hand. Okay, so I don't specifically like this classification, but if you have you're working, for example, in Canada, in, I don't know, North Quebec, you can do a model analysis just by looking at the rock because they are absolutely fresh. There is no alteration. So maybe in Siberia, you may have something like this where you can use this table. But if not, I created this classification in 1997, and it's a very simple way of getting to the name of the rock. And I don't know if I can make it bigger. Let me see. Oh, yes, I can make it bigger. So we start with the sample and we ask, is the sample dark? If it is yes, is the sample heavy? Yes. Does it have volcanic texture? No. Does it have more plagioclase than pyroxene? Yes. Well, this is an anorthosite. This is very, very, very simple way of getting to the name of the rock. Another example, let's say it was not dark, but it was heavy. Then we add the qualified leuco. Okay. Does it have voids? Let's say yes. Does it have a volcanic texture? Yes. Then it's a phonolite. Okay, so using this table, you can get to all the basic names of the igneous rock. And I add this graphic because we are humans. We are very bad at estimating the amount of percentage of certain minerals. For example, that is 50%. And for me, when I look at that, for me, that is 100%. Okay, so I put this to help you define what is the percentage. So if we were going down this way, if Calispar less than 35%, that's how it's gonna look. And we have a volcanic texture, then it's a dacite. If not, it's a granodiorite. So this method, this table, which by the way is in the book that I mentioned at the beginning, will help, will help you determine the name of the rocks. And again, remember, there are root names when you're absolutely sure, or approved names. An approved name, you just add an hyphen and the word rock. For example, granite is is a root name. Granitic rock is an approved name. When you are not sure, use an approved name. Later on, when you get the thin sections, you will be sure, okay, this was granite, then you use the proper name. So you have this flowchart for igneous rock, for volcanic rock, consolidated or not consolidated. Again, this is very simple. You have less than 25% of pyroclast, and the size is from 2 to 0.032 millimeter. That is a volcaniclastic sand. And you can see it's bold and underlined. That is an approved name. Okay, so, and if it is consolidated, Well, you get down there, the same thing is a volcanoclastic sandstone. Okay? So that is unconsolidated and consolidated. This table, this is part of the quality assurance. You got this in your Rorschach. Every geologist has a set of this. Everybody's going to be naming the rocks the same way. Same thing I did for the sedimentary rocks. And again, I think I can, oops, no. 1, 2, 3. I did the same thing for the sedimentary rock. I'm going to make this a little bigger. So you take the sample, test it with ACL. If it reacts, everything to the right or left in green is yes, down, red is no. Let's say no, it doesn't react to ACL. It's heavy, yes, then it's a dolomite. If not, it's heavy, it has oolite and noodle, well, it's a phosphorite. So you see, it's very simple, easy way of determine the names of the rocks. Metamorphic rocks, same thing. These are very simple questions. So take the sample. If it is non-foliated, then you add the qualifier meta. So it may be a meta-granite, a meta-diorite, etc. If it is foliated, it has a lot of hornfels material, then it's hornfels. If you see the visual grains, then it's a granophyls. If there is some schistosity, then it's a gneiss. If there is no schistosity, no scar, you see carbonate, then it's marble. So you can see every single type of rocks, even those more difficult, like the differentiating between a protomilonite and orthomilonite or a classical ultramilonite. All this is very easy, just yes, no questions to very simple, yes, no answers to very simple questions. Okay, so that was the name and the qualifier. So now we're going to talk about the mineralization, because the texture is a little bit more complicated. So mineralization is basically the same thing as the alteration. We have the same type of classification: pervasive, selective pervasive, veinlet, etc. So P9 PY means 90% pervasive periodization, for example. And it's the same. You have a dash, or in this case a plus, a plus symbol, it means the two together. You had a semicolon, it will be a progression. Now, let's talk about textures, because this is, remember for you, the guys that study Russia, is structure, but we're talking here. So again, I have created this, I call it the igneous rock texture identifier. It's composed of 5 sections, very simple to use. So you start with the first one, you take the sample. If it has volcanic fragments, then it's a pyroclastic. If you go to the section of pyroclastic, it's section 2. If this crystal can be seen without the aid of a lens, then it's phaneritic. If you need a lens, even with a lens you cannot see it, then it's classic. If not, it's aphanitic. So the first case depends, very simple, depends on the size of the blocks. So you have from quartz blocks and bomb down to fine ash, just by the size of the thing. Now, this one is more complicated, and you will be using this all the time, especially you're working with in felsic rocks. And you all remember this definition as like epidiomorphic or allotriomorphic or anhedral. You know how difficult it was to remember all that? Well, it will be very simple with this graphic. So the sample, does it have a general orientation? Let's say no. Does it have vacuoles? Let's say yes. Are the vacuoles filled? Then it's amygdaloidal. Let's say it was not filled and it has no ramification, then it's vesicular. Okay, let's say it doesn't have vacuoles. All the grains are anhedral, the same size. Then you add the classifier, the qualifier allotriomorphic to whatever name you find next. So let's go this way. All the grains are the same size, so I will add allotriomorphic. There is the distinct alienation. I will add the term fluidal. Then the phenocrystals are much larger than the ground mass. Let's say yes. Let's say the ground mass is phenolitic. Let's say yes. So we have an allotriomorphic fluidal porphyry texture or structure for you. See how easy it is? You need this table. I mean, you will use it all the time, and hopefully there will be a moment that you will remember all this by heart. I never done. I just keep it because for me it's much easier to just look at the. For me, it's much easier to look at the table. And section 4 will be the glassy textures. And this is very simple. Is the rock completely entirely by glass? Well, that's an obsidian. Okay. If it's not, if it has luster, waxy, then it's piston. That way you can do it. And when you want to describe the aphanitic part of a porphyry rock, then you use this table here and say, are the phenocrystals, are there phenocrystal in the ground mass? So normally you have the phenocrystal, you have the ground mass, but sometimes the ground mass have some phenocrystals too. So that will be a porphyrophanitic texture. Okay? Or phylotaxitic or glomerophytic. So all these very difficult names to remember, with a very simple flowchart, you will be able to do the classification of the texture. Now, let's see some examples. Okay, so that rock there, the full description, okay, the one that you will do in the field, you say, well, it's a disseminated kaolinitic alteration, quartz-bearing plioclast-rich granodiorite. Now, I stop there. Granodiorite is bold and underlined. That means it's a root name. Notice that the qualifiers are qualifying the amount of quartz bearing. That means there is a little quartz, but it's a lot of plioclast. The most abundant mineral will be the closest one to the name. If quartz was more abundant than plioclast, then it will be plioclast bearing quartz-rich granodiorite. Notice also that there is the hyphen between the quartz bearing plioclast rich, but there is no hyphen between the qualifier and the root name. That's the only rule. It's very simple. Then the texture is allotriomorphic, granular porphyritic with disseminated limonite from pyrite. That is the full description. And here will be the code. If you are in the field and you prefer to write code, this is basically what you will be feeding in the computer. And this is how it looks when you just handwritten. Okay, remember, the qualifiers is between quotation marks, the root name will be underlined, and the rest is just your handwriting. Let's see another example. Full description, it says selective pervasive chloritic, magnetic, plioclast olivine ferric basalt. Okay, this is porphyry. So we describe the phenocrystals first. And again, the most abundant phenocrystal will be close to the name of the rock. It's a basalt. We are sure it's bold and underlined. It's a porphyry texture. and it has disseminated pyrite and magnetite. This is how the code will look, and this is the handwritten. And one last example. Okay, here we have a pervasive silicification, strongly magnetic, olivine-rich basalt, pilotaxitic, disseminated pyrite and magnetite. This is the description. And as you can see, this kind of description covers everything. The alteration, the name, the qualifier, the texture, and the mineralization. If something is missing, let's say there was no mineralization, then you just stop here. Pilotaxitic texture. That's it, nothing more. You don't need to write what is not there. So I think, of course, this will be great if I was in front of you and we will have samples in our hands and we will discuss all the things. This is just a webinar presentation just to make you aware of what is available, what is there. My book is a very simple way of learning the thing. I strongly recommend that you go to the British Geological Survey and read the whole description. Maybe you can come with a better way of doing the description. Whatever it is, it must be recorded in words or in a video, and you must insist that all the geologists will use this. This is part of the quality assurance. Quality control is easy, quality assurance is very difficult, and it's the one that will guarantee the success of your exploration work. So that's it. Again, the name is Ricardo Valls from Valge Consultant. You have there actually the link for the book, which I strongly recommend you to get. And thank you for your time. Thank you, Anton, for giving me the opportunity of presenting this very important part of our geological work, quality assurance, quality control for everybody. Until next time, have a great day.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.